Hello everyone. Today we are going to dive into one of the most powerful frameworks in modern physics. It's statistical mechanics. At our macroscopic scale, we can see that fluids flow smoothly like air, a river, temperatures stabilize, and pressures are predictable. But if we zoom into the subatomic scale, there is utterly chaos. Billions of atoms colliding in different speed. How does microscopic chaos give birth to absolute macroscopic order? The secret bridge is statistical averages. Today we will see how a simple logarithmic bridge, which was discovered by Boltzmann, connects individual quantum states to bulk thermodynamic parameters like entropy, pressure, and temperature. Before we move forward, let us understand where we stand in the landscape of physics. Before we go to study the statistical mechanics, we should know what mechanics is. Actually, the mechanics is the fundamental branch of physics which is dedicated to the study of motion and the forces that produce it. It forms the foundation upon which all other branches of physics often are built. Now, to model reality, we use three distinct lenses to see our universe. If you are designing an aeroplane wing or structural beam, you use classical mechanics, the lens of macroscopic object. If we are going to design a semiconductor device or a quantum computer, we look through the lenses of quantum mechanics. But what happens when we have a system that is both complex and contains a massive number of constituents like a mole of gas or free electrons in metal? Quantum mechanics become too localized and the classical mechanics fail to scale. That's where statistical mechanics comes in. It is specifically toiled to negate the behavior of the complex many. Let's look back at our classical roots. In 1687, Sir Isaac Newton gave us a clockwork universe. Under this framework, space and time are absolute, flat, and unwavering. Classical mechanics operates under the rule of certainty. It's a strict deterministic. If I know the exact initial position and velocity of a projectile and the forces acting on it via F equals to ma, I can use calculus to precisely map out its path anywhere across the time. It's beautifully predictable, but this rule of certainty holds a trap when system goes large. Here is where the classical system breaks down. Newton's laws work perfectly for tracking a single projectile or even an entire planet. But what if we try to apply it to a container of gas? For every single particle, we need equations for its position and momentum. If you have n number of particles, you have to track n simultaneous equations. Is it practically possible to calculate this? No, it is mathematically impossible to solve for macroscopic system. But more importantly, do we actually care about the exact velocity and of molecule number of the order of 10 to the power 14 at any given millisecond? Absolutely not. We only care about the average system properties like the overall pressure which is pushing against a piston or the temperature of the gas. Let us quantify this classical crisis. A mole of gas contains roughly Avogadro number of particles, which is of the order of 10 to the power 23. To track them classically, we, we would need to write down and solve 10 to the power 23 coupled differential equations simultaneously. No supercomputer in existence, or perhaps ever to exist, can process this. It is mathematically intractable and engineering-wise useless. The statistical solution is a paradigm shift. Instead of tracking individual trajectories, we shift completely to probability distributions. We build a mathematical framework to derive our macroscopic parameters like temperature, pressure, entropy strictly out of the collective statistical behavior of those unobservable microscopic atoms. Let's formalize how this mapping looks. On the microscopic side, parameters like hyperdynamic, particle positions and velocities are constantly fluctuating due to collisions, making them impossible to pin down. On the macroscopic side, things are beautifully steady. When a gas reaches thermal equilibrium, its temperature, pressure, and volume become consistent that we can measure with simple gauges. Statistical mechanics provide the exact probability laws that link these two worlds together, bypassing the impossible task of tracking individual velocities entirely. To handle this mathematically, we need to build a new geometric environment which is called phase space. To fully define the state of just one single particle, you need 6 dimensions, 3 coordinates for its position x, y and z, and 3 for its momentum vector px, py and pz. This 6D space is often called microspace, where a single point captures everything about one particle. Now, let's scale up to the entire system of n particles. We construct a massive hyperdimensional universe which is known as gamma space. It has 6n dimensions. Think about the elegance of these. Instead of tracking billions of bouncing particles, an instantaneous state of your entire system is represented by just a single phase point moving through this 6n dimensional space. In classical physics, you could subdivide this phase space infinitely, but when we include quantum mechanics, nature throws up a hard barrier which is known as Heisenberg uncertainty principle. It states that delta x into delta px should be greater than equals to h, where h is the Planck constant. You cannot know both position and momentum with infinite precision at the same time. Because of this, phase space is not a smooth continuum. It is pixelated into elementary cells. If we multiply the uncertainty across all three spatial axes, we find the minimum possible volume of the phase space cell is exactly h cube. This is a monumental insight for us. This h cube volume serves as the absolute fundamental pixel size of the universe. It transforms state tracking from a messy infinite continuum to a clean discrete counting exercise of quantum states. Let us discuss two fundamental definitions that you will see on every derivation: the microstates and the macrostates. A macrostate is the large-scale thermodynamic condition of the system. It only requires a few bulk variables to be perfectly well defined, specifically its total number of particles, volume, and the internal energy. On the other hand, a microstate is the most hyper-defined description which is imaginable. It is the exact instantaneous snapshot of which specific particle is sitting in which specific phase space cell at an exact moment. It requires all 6n coordinates. Crucially, remember that many different microstates can result in the exact same macrostate. To do calculations, we rely on the fundamental pillar of statistical physics, the postulate of equal a priori probabilities. It simply states that if a system is isolated and in equilibrium, all accessible microstates that satisfy the microstate constants n, v and u are equally likely to occur. Nature does not favor one specific particle arrangement over another. If they are energetically allowed, they have the exact same probability. This equal probability rule allows us to use combinatorial mathematics to predict system evolution. Let us visualize this using a simple example. Distributing four distinguishable particles, let's call them A, B, C and D, into two halves of a container. If we look at the top macrostate where all four particles are packed into the left side, there is only one possible microstate that can achieve this. If we look at a 3,1 split, there are four ways to arrange it. But look at the bottom row. A perfectly even 2,2 split can happen in 6 distinct ways. The number W is called thermodynamic probability. It is not a mathematical probability bounded between 0 and 1. It is a massive integer counting how many microstates support a specific macrostate. When we scale up from 4 particles to a system where n is of the order of 10 to the power 23, these numbers explode exponentially. The number of ways to arrange n total particles into various energy levels containing n1, n2, n3 particles is given by the standard permutation formula W equals to factorial capital N divided by n factorial n1, factorial n2, factorial n3 and so on. Because factorials grow astronomically fast, W, the thermodynamic probability, reaches unimaginably massive numbers. The most probable macrostate, which represents true thermodynamic equilibrium, is simply one that is supported by the overwhelming largest number of microstates. This explains the arrow of time and spontaneous physical processes. If you start with a gas clumped up in a container, that macrostate has a very low thermodynamic probability W, meaning very few microstates can create that configuration. As particles randomly collide and move, the system naturally wanders into macrostates that have higher and higher counts of microstates. It will end up in the macrostate with the maximum number of W, which is uniform distribution or what we can call equilibrium. The system does not move there because it's forced by a macro potential. Rather, it moves there purely because the equilibrium state has vastly more ways to exist. This brings us to the Holy Grail equation carved onto Boltzmann's tombstone. S equals to Kb into natural logarithm of W. This equation is the Rosetta Stone of modern physics because it directly bridges the macroscopic with the microscopic. On the left hand, you have entropy, a classical measurable property representing thermodynamic disorder and energy unavailability. On the right, you have W, a purely microscopic count of discrete quantum states. The natural log ensures that while microstates multiply when systems combine, their entropies add up cleanly. The Boltzmann's constant, which is Kb, acts as the physical scaling factor that translates microscopic state counting into macroscopic thermal units. Let's explore the profound implication of this bridge. The second law of thermodynamics states that the entropy of the universe always increases. Why? Under statistical mechanics, it is just a matter of probability. The universe moves towards the higher entropy simply because high entropy states have drastically more microstates available to them. This is also beautifully explained in the third law of thermodynamics. At absolute zero, thermal disorder completely vanishes, meaning the system settles into perfect order, exactly one single unique ground state, that is W equals to 1. Substitute W equal to 1 in this equation and natural logarithm of 1 gives us an entropy of exactly 0. Now that we have the state counting tools, how do we apply them to different physical entities? The field divides into a clear hierarchy based on the nature of the particles. If your system can be modeled using classical approximations where particles are distinct and distinguishable like gas molecules in a engine cylinder, we can use Maxwell-Boltzmann statistics. The particles follow these statistics are known as bosons. However, if we are working with subatomic configurations where wave functions are overlapped, particles become fundamentally identical and indistinguishable. This forces us into quantum statistics, which split into another two distinct paths, the Bose-Einstein statistics for those particles with integer spin and the Fermi-Dirac for the particles with half-integer spins. The particles obey Bose-Einstein statistics are known as bosons, and those follow the Fermi-Dirac statistics are known as fermions. Let's reinforce this key distinction because particle identity strictly dictates how phase space can be occupied. If particles are identical but far enough apart that we can tell them apart by their trajectories, they are distinguishable and we can use classical Maxwell-Boltzmann statistics. But in quantum domains, particles are completely indistinguishable. You cannot point a level on an electron. If they have integer spins like photons or liquid helium, they are called bosons and they follow the Bose-Einstein rules. If they have half-integer spins like electrons or protons, they are fermions governed by the Fermi-Dirac rules, meaning they must obey the Pauli exclusion principles. To find out exactly how energy is shared among a collection of particles, we use a universal mathematical structure which is written as n epsilons equals to g epsilon into f epsilon. Let's break this down into simple terms. G epsilon is the statistical weight or the density of states. Think of it as the number of available chairs at a specific energy level epsilon. F epsilon is the distribution function. It represents the probability that any single chair at that energy level will actually be occupied. Multiply them together and you get n epsilon, the total number of particles that will successfully settle into that energy state. Our next goal is to see how this probability function f epsilon changes for our three different types of statistics. Here are the final mathematical signatures for the three statistics and notice how remarkably similar yet functionally distinct they are. For Maxwell-Boltzmann or MB, the probability function is a simple exponential decay curve. That is, fmb epsilon is equals to 1 by e to the power beta into epsilon minus mu. Look what happens when we shift the equation for Fermi-Dirac. A simple plus 1 is added to the denominator. Mathematically, that plus 1 guarantees that the function can never exceed 1. This enforces the Pauli exclusion principle. You can never have more than one fermions per quantum state. Conversely, for Bose-Einstein statistics, we introduce a minus 1 to the denominator. This subtraction shrinks the denominator, driving the occupancy probability up and mathematically encouraging bosons to crowd together into the exact same lowest energy state, giving rise the phenomena like lasers and Bose-Einstein condensations. This is a summary for your reference and exams. Let us review the key contrast. Maxwell-Boltzmann or the MB particles are distinguishable, have any spin, ignore Pauli exclusion principle, and features negligible wave function overlap. Classical gas molecules are the perfect example of this type of system. Bose-Einstein particles or the bosons are indistinguishable, have integer spin, ignore Pauli exclusion principle, and feature significant wave function overlap. Photons and alpha particles are the example of such examples which are follow such distribution. Fermi-Dirac particles or the fermions are indistinguishable, have half-integer spin, strictly obey Pauli exclusion principle, and feature significant overlap of wave functions. Example of such particles are electrons, protons. Let's take a close look at each one, and starting with MD statistics. MB statistics were developed to describe identical but distinguishable weakly interacting structureless particles, often called bosons, under high temperature, low density condition. As you can see in the MB scattered grid, because these particles are treated classically, they can be uniquely tracked and have no spin constraints. There is no Pauli exclusion limit, meaning any energy state has an unlimited capacity and can accommodate an arbitrary number of particles simultaneously. How do we derive the actual distribution law for this type of statistics? We start with our conventional expression for thermodynamic probability W, and we maximize natural log of W subject to two physical constraints. The total number of particles must remain constant and the total energy must remain constant. Using the method of Lagrange multipliers with constants alpha and beta, we arrive the classical MB distribution law. Ni equals to Gi divided by e to the power alpha plus beta epsilon I, where Ni is the number of particles in a state, Gi is the number of sublevels, and epsilon I is the energy. Now look closer at the application form of the law, where we write it as n epsilon equals to G epsilon into A into e to the power minus epsilon by kT. This is the fundamental tool for analyzing the behavior and the energy distribution of an ideal gas. However, as engineers, we must understand its failure conditions. It breaks down completely at the quantum level. It cannot explain the behavior of photons in blackbody radiation, nor can it correctly predict the specific heat and electrical conductivity of free electrons inside metal. For those systems, classical assumptions fail and we must transition to quantum statistics. The analytical curve of the MB energy distribution governed by this integral equation shown inside the box. Look at the shape of the curve shown below. It rises sharply, hits a peak at the most probable energy, that is kT by 2, and then develops a long tail tapering off to the right. A key insight from this distribution is if you integrate across the entire curve to find the mathematical expectation, the average molecular energy is exactly 3 by 2 kT. Take note of this critical detail. This average energy is determined entirely by temperature. It is strictly independent of the molecule's mass. A light helium atom and a heavy xenon molecule mixed in thermal equilibrium will possess the exact same average kinetic energy. Now, what if we want to know the distribution of molecular speed instead of energy? We substitute epsilon equals to half mv square and delta d epsilon equals to mv dv into our previous formula to yield the speed distribution law, which is uh, written here. Nv dv equals to 4 pi n multiplied by m by twice by kt to the power 3 by 2 into v square e to the power minus mv square by twice kt into dv. This formula represents a balance between two competing mathematical terms. The v squared term creates a parabolic rise that drives probability up as speed increases, but the e to the power minus mv square by twice kt term act as a heavy exponential decay anchor, eventually pulling the probability back down to zero at extreme speed. This graph shows how temperature changes ideal gas dynamics. Look at what happens to the curve as temperature rises from T cold to T hot. As temperature increases, the thermal energy shifts the entire curve to the right, increasing the average velocity of the molecules. But because the total number of particles is constant, the hotter curve must flatten out so that the total area underneath remains exactly the same. It also marks the distinct location of the most probable energy, that is EMP, and the average energy, that is E average, along the distribution. This speed distribution profile highlights what I called the speed trifecta, that is three distinct mathematically defined velocities that characterize an ideal gas. The most probable speed, that is Vp, is equals to square root of twice kt by m, is the speed at very peak of the curve. The average speed, which is V average, is equals to square root of 8 kt by pi m, which pulled slightly to the right of the peak by the long high-speed tail. However, the root mean square speed, that is Vrms, is equals to square root of 3 kt by m. It is the velocity most directly related to the gas's kinetic energy weighted by the high-speed outliers. This provides the visual and mathematical proof of the permanent relationship, that is Vp is less than V average is less than Vrms. Let's move into the quantum domain and examine the Bose-Einstein statistics. This framework governed identical, completely indistinguishable quantum particles that possesses integral spin angular momentum such as 0, 1 cross, 2 cross, and so on. We called these particles bosons, and the classic examples include photons and phonons. Look at the Bose-Party graph. Because these particles are indistinguishable and their wave functions are completely symmetric, they have infinite capacity. The Pauli exclusion principle does not apply here. Any arbitrary number of bosons can crowd together into the exact same quantum state. The derived mathematical distribution law for Bose-Einstein statistics is written here. Here, mu represents the chemical potential of the system. Notice again that negative 1 in the denominator. As the energy state epsilon I approaches the chemical potential, that denominator becomes small, which causes the occupancy number Ni to increase. Let's look at how this shapes real-world phenomena. The primary real-world application of BE statistics is analyzing light and radiation. Think of photons inside a black body cavity. Photons are spin-1 bosons that are continuously emitted and absorbed by the cavity walls. It means that their total number is not conserved. When we apply BE statistics to those photons, the derivation directly yields Planck's law of radiation. The energy expression is written here in the left hand side. On the right hand side, the Bose-Einstein statistics also predict an unusual state of matter which is known as Bose-Einstein condensation. When you take gas atoms that are bosons and cool them down near absolutely zero to a critical temperature Tc, their individual thermal wavelengths expand and begin to overlap. Because bosons favor occupying identical states, a macroscopic fraction of the atoms drops into the lowest energy ground state simultaneously. They lose their individual identities and merge into a single macroscopic quantum wave governed at t equals to 0k by this ground state particle relationship written here in the bottom of this slide. Let's turn to our second quantum framework, which is known as Fermi-Dirac statistics. Developed by Enrico Fermi and Paul Dirac in 1926, this framework applies to identical indistinguishable particles with a half integral spin like half h cross 3 by 2 h cross etc. Which we call fermions. That means the particles which follow this type of statistics are known as fermions. Example of fermions are electrons, protons, neutrons like particles. Look at the Pauli bouncer graph. Fermions have antisymmetric wave functions and must strictly obey Pauli exclusion principle. This means cell capacity is absolutely limited. A single phase space cell can only hold either 0 or 1 particle. No crowding is allowed. Each particle requires its own slot. This strict exclusion rule gives us the Fermi-Dirac distribution law, which is written in the bottom of the slide in left right hand side, where epsilon f is a key reference parameter known as the Fermi energy of the system. That +1 in the denominator changes how this system behaves compared to the other two distributions, especially at low temperature. Let's examine how this law governs solid-state materials. Fermi-Dirac statistics explain the internal behavior of metals. Conduction electrons inside a metallic crystal lattice act as a free electron gas of fermions. Because they obey the Pauli exclusion principle, these electrons cannot all drop into the lowest zero energy state when cooled. Instead, they fill the available energy slots sequentially from the bottom up like water filling a bucket. The highest occupied energy level at absolute zero is the Fermi energy and denoted by EF. This creates a high mean internal energy, that is E average equals to 3 by 5 EF, generating an immense macroscopic degeneracy pressure that stabilize metallic structure and keep stars like white dwarf from collapsing under their own gravity. This overlay graph shows the distinct shapes of three distribution functions by plotting their occupation index against energy. Look at the Fermi-Dirac function, which is shown in copper colored line. At t equals to 0k, it forms a perfect step function maintaining an occupancy of exactly 1 up until the Fermi energy and then dropping straight to 0. For Bose-Einstein statistics, which is shown in cobalt blue, the low energies, it shoots up, showing how particles accumulate in the ground state. And for Maxwell-Boltzmann, the graph shows in charcoal black color, it acts as a baseline exponential decay curve. But notice what happens at higher energies on the far right. All three curves begin to merge. Let's explore why that happens. This brings us to an important boundary condition, which is known as the classical limit. While the quantum statistics are required at high densities and low temperatures, look at what happens when temperature rises and density drops. At high temperature and low density, the physical distance between individual particles becomes much larger than their thermal de Broglie wavelengths. Mathematically, the term exponential beta into epsilon minus mu becomes much larger than 1. This makes the plus minus 1 modifier in the quantum denominators negligible. As a result, both FD and BE collapses into the classical MB distribution. This shows that the Maxwell-Boltzmann is the universal high temperature limit for all matter. Let's look at our first application. It is modeling conduction electrons in a metal as a free electron gas using FD statistics. As we discussed, because electrons are fermions, the Pauli exclusion principle prevents them from gathering in the lowest energy state at absolute zero. They stack upward into available state up to the Fermi energy. This leads to a key result. Even at absolute zero, the electron gas possesses a high mean internal energy equals to 3 by 5 EF. This internal energy is what determines the electronic contribution to heat capacity and electron conductivity in materials selection. Our second application is understanding the mechanism behind Bose-Einstein condensation. Consider a gas made up of identical bosons. At high temperatures, they act as individual classical particles. But as you cool the gas to a critical temperature, the Broglie wavelength expands. When this the Broglie wavelength becomes roughly equals to the physical distance between the particles, their wave functions begin to overlap. Because bosons favor occupying identical states, a large fraction of the atoms drops into the single lowest energy ground state simultaneously. The entire gas then begins to behave as a single macroscopic quantum entity, which forms the basis for superfluids. Our final application for today's returns to Planck's law of blackbody radiation, viewed through the lenses of state constraints. Consider an open cavity filled with photons in thermal equilibrium. Photons are spin-1 bosons, but they have a unique constraint. They are continuously created and destroyed by the cavity walls. This means their total number is not conserved. In our mathematical optimization derivation, this requirement forces our first Lagrange multiplier, that is alpha, which relates to chemical potential, to equal exactly 0. That means alpha equals to 0. Applying the Bose-Einstein distribution with alpha equals to 0 directly yields Planck's equation. This shows how statistical mechanics correctly predicts the emission spectra of everything from industrial lasers to stars. This concludes our module on statistical mechanics. Thanks a lot for your kind attention.